Hello, everybody. Thank you very much, Frank, for this very kind introduction. Thank you, Dorsten, for giving this introduction as well. I'm very glad that we can host the Data Geeks meetups again. And I'm very, very thankful to all the people who have come to hear me talk about the most exciting topic in the world, documents. And in particular, input management of documents. So Frank already mentioned we have our own workflow solution, this CIB flow, where we build business processes. So internally to companies, documents are used in a variety of ways, and these business processes, they have their own modules handling the documents. And we have this new developed fork, CIB7, and currently I'm quite sure a lot of you don't really know what a business process is, so I want to try to make it more concrete. So this is the inbox process, or the input management process. It's something the AI team puts a lot of work in to make it really good, and it's about a company who gets mail. And almost all companies and other organizations get mail. They get mail from a variety of sources: email, physical inbox, and nowadays often via apps. And the process does a lot of automatic document preparation. And after the automatic document preparation is done, we go into our AI modules. We have two big AI modules in working there, and I want to introduce you to both of them, but my talk is mostly about the first one. CIB recognize our classification system. After documents are classified, so you found out what type of document it is. For example, it could be a salary statement, or it could be a driver's license. There are a lot of different documents that could be in use. You can use a special extraction tool to that is fitting to this particular document. And this is the second part. So how do you usually train document classifications? So AIs have a lot to learn, and I mean this literally. Usually the approach is a document exists, and it's a very complicated software object, and maybe a very complicated cultural object, actually. And when we do the classification, we tend to do something like we use a complicated feature that should describe everything about the document. Like we use the whole image of the document rendered, or the whole text of the document. And then AIs are trained on a large data set with millions of documents, and they form their own abstract features from these very complicated input features, and then use these features to do abstraction. And since everybody is doing it this way, we started out doing it exactly the same way. We tried to do document classification with a semantic vector and trained the classification network on it. And of course, this did not work. The message is, if you have a really complicated document system, this usually doesn't work, even if you try a lot of different embeddings and do all the stuff. And like Mike Tyson says, everybody got the plan until they get punched in the face. So the result was we got an accuracy about 80%. Sounds good, but this means 20% of the time, somebody working the process has to correct the AI. It means a huge amount of manual labor. And since we were automatizing our own inbox process, it meant a lot of firm feedback from our own workers who had to correct this. So, and of course, the people working at CIB, they are much smarter than an AI. And I don't mean this in a bad way, they really are. They use a lot of things that the AI doesn't have access to, because the AI on its own had to learn all these things about documents, whereas humans have a big advantage. Humans are a social species, and they talk about stuff. And they have a lot of concepts that they use to find out what type of document something is. Like they say, there are fonts, or the document has a layout in some way. So there are specialized features that humans have learned from other humans that make it much quicker to classify something and much more accurate. What nobody does, no human on Earth, to classify a document is read it completely. I mean, most people don't read documents completely. But yeah. So I had a plan. We will do the same for the AI. We will, in some way, prepare expert features that are capable to abstract the document completely. And these extra features will then solve all our problems. And I thought it was actually quite easy because we are a document company. So then I started a huge journey. And the journey starts with how do features usually get into an AI. I think this is something that people are kind of hazy about. The trick usually is an AI just needs a bunch of numbers. So you have to think about a way of writing whatever your property you have as a bunch of numbers in a row, and then call it a vector. And so you have your feature. And if you have multiple of these features, there are ways of combining them. There are several different ones, but the most simple way is just concatenating the two vectors together, and you get a bigger vector. It's a vector. And here I've used two examples, text and fonts. So how would you make a vector out of the fonts of a document? And the answer is you use AI. We use another AI, a CNN, and we cut out each of the words that we have segmented from a document. And the CNN then detects the font for each word, and we just count the font types. And once we counted the font types, we get a vector that is defined this way. 100 words were Arial, 200 words were Times New Roman, and so on. And you get a very long feature vector because we can recognize many different fonts with the CNN. Then another feature is much more involved. It's a variational autoencoder that we trained in another research project. And the idea is here, you have a network that learns to reduce the size of a document to a very small bunch of numbers. It goes over the whole document, and for each tile of the document, it just says this tile is now represented with one integer number. And then there's another AI that again tries to reconstruct the original image of the document from these numbers that represent the patches, and is then punished or rewarded depending on how good it did the reconstruction. And this produces a very small abstracted version of the document that we can use as a feature. Then there are a lot of semantic features that you can extract from a document. I mean, for example, if a document contains the name of Frank or somebody like that, you know it's an important document and it could be classified in this class. And there are other such words that we use usually to classify. And you can just count how many of these words were occurring, and then you have another vector. Sometimes there are no important words, then it's a zero vector in this case. Another more involved way of getting a feature is a so-called BERT network. This is maybe known to some of the people who do a lot of AI. The basic idea is the network is trained on a text just like this one, where some stuff is left out, and the network has to estimate what the correct word is to put here based on the rest of the words that are in the sentence. And these kinds of networks in their later layers, they have a bunch of numbers, and you can use these if you add them together as another vector that you can input into your system. So, and we did this for a bunch of different vectors. I can't go into all of them today, and build this system where you at first dispatch, then you calculate all these vectors, and then you do a fusion and get a big vector representing the entire document. And this big vector is something that is quite hard to grasp for a human. It's a 4,000 dimensional vector that represents basically most of what there is to know about the document in some abstract fashion. This leads then to a question: how can we make sense of these vectors? And I try to make sense of these vectors with a customer data set here, where the customer doesn't have that many documents that are labeled, because labeling documents is a lot of work. So I calculated these features for these different types of documents. And you can see each of the colors here represents one of the types of documents that is used. For example, Ausweis, it means DNI or something like that. Gehaltsnachweis is a salary statement. ZB2, it's a car registration document. And so how can we now make sense of the 4,000 dimensional vectors? The idea is using dimension reduction techniques. This is sometimes known to people who do a lot of stuff in genetics. The reasoning is these vectors, if you imagine 4,000 dimensional space, are not spread out evenly over the space. But actually there are surfaces that can go through the space, and you can find surfaces that are containing most of these vectors, and then you have coordinates within these surfaces. And using these coordinates, you can project them down into radically smaller vector spaces, like two-dimensional vector spaces in this case, where I used the 4,000 dimensional vectors and visually represented them in 2D. And the interesting result here is that without any classification effort on my part, the vectors found out that it have to put the ZB2 up there, for example. And there were other results, like the Ausweis documents, they were in the middle, and the salary statements, they built two clusters, and then we looked into it, and there are two different types of salary statements exactly in our document case. So this led us then to create a classification system for the customer. And we only had 631 pages originally. Most of them were contract pages. So the hard stuff was separating them first. We did this with the same approach, using vectors for the contracts. And after some algorithmic post-processing on our test sets, we achieved a 100% classification accuracy for contract statements versus other documents. And then in the second part, we didn't have enough documents to do a strong statistical analysis, but since we didn't really estimate any parameters, we could say outright we have about 94 or something like that % probability of being correct. You see a confusion matrix here. And the more numbers are on the diagonal, the better it is. And there were very little numbers who were not on the diagonal. So good classification out of the box without any training, just by using documents that vectors that abstract the documents completely. So then we went on. We had another project partner, which I find was quite an interesting project partner. They wanted to find fraud in physical billing. And the idea was kind of different physicians, they produce different documents for invoices. And each physician kind of has his own fingerprint on these documents. And the idea is, even if somebody was to fake an invoice that is correct in the sense of all the numbers add up and so on, if they don't have a good example of the invoice of the person he is faking it for, they would make a document that looks very different from them, something we could immediately detect with our document feature vectors that we then started calling fingerprints. And the result was, yes, that's 100% correct. Calculating the feature prints leads us to a result where each of the physician bills that I colored in a different color was almost completely separated from the others. And we get these clusters with direct separation between them. And of course, somebody did something strange and one of them jumped out of line. So it's not perfect, but it really captures something about the way different people produce their documents, if it's the same type of document. And I have a catchy title here. It's Catching Frauds with Topology. That's why we used some features of the layout topology in the vector. The idea was here, each of the words has coordinates, and depending on whether you say words that are far together, far apart, or those that are close together form a unity, you get different topological features of your document layout. And if you vary the scales, these topological features change. And the scale variance that you can calculate in these kinds of dots, which we vectorized. And it increased the separation considerably between the different layouts of the individual physicians. So we come back round circle to the CIB mailbox. And the CIB mailbox is much harder than the other customer projects we had at the time. We were very confident. We have this new system. We tried it on a bunch of stuff. It worked really good. And then we go to our own stuff, and it doesn't. Classifying out of the box without any additional measures using clustering doesn't work well. You only get to about 88%. There are, of course, reasons for this. We have a very varied mailbox in different countries. It's highly multilingual, and different countries have different document systems, so it's complicated. But we were kind of unhappy about this. So, of course, we want to classify our own mail as well. And so we began analyzing the whole thing, and we did these UMAP diagrams of our own inbox, where we have a lot of labeled data. And if you look at it, it looks not like the ones that I have shown you before. It looks completely chaotic. And there are reasons for this chaos. So there is an output class that is called Schriftverkehr. And Schriftverkehr is hard to translate for me, even as a native speaker. I think the best translation is something like whatever. And this Schriftverkehr, of course, intermingles and messes with all the clusters that we could possibly have here. And at first, despair hits us and so on, but then we start looking at the UMAP more precisely, and we realize something. Even though the Schriftverkehr makes the clusters really hard to directly pick up, you see something like this. Here the contract documents, for example, they go together. And here the invoice documents, they also go together. So there is some closeness there, there is some signal there. We could use them, but what we cannot use is just using clustering. You need more parameters to make the separations. So we trained a neural network on it. And it was just a 5-layer MLP. And it increased the classification accuracy considerably again. And the basic idea is, if you just use some stupid feature vector, this is about as good as you get on this kind of data. It doesn't have enough information about the document, and you get, this is a broad type embedding with a classification head. It just doesn't work as well. You can increase the accuracy by using the fingerprints and the clustering. Interestingly, the features just beat out the parameters in this case. But the strongest is, of course, combining both worlds. Fingerprint plus AI gives us a classification accuracy in this case of about 94%. I mean, people could now say 80%, 94%, what's the difference, who cares? You have to always think about it the other way around. If somebody has to correct the AI 4 times more, it's a lot more work. So a system that marginally reduces the remaining error is very valuable in this case. And in this case, it reduces the remaining error by a factor of 4. Yeah, so we talked about the classification. Now I want to quickly talk a bit about our entity extraction. the entity extraction system is something that necessarily comes after the classification system. So the idea is you have these different document types, and some document types should be extracted with different information in mind. So the basic example is if you have a car registration, you often want to extract information about the car. But if you have a contract, you don't want to extract information about the car. Most of the time, inside the contract, there is no information about the car, other in cases where the contract is about car sales or something like that. So different type of input into the company require a different set of things you want to recognize. And then there is another reason. Different types of documents require a different technology to extract. So a lot of people think about extraction in basically I have my favorite technology. It's my hammer, and I try to strike everything down with it. But we don't feel this is the correct way. So we built a multi-headed or mixture of expert classification system that after the classification happened, we have the best expert for the type of document that is used. And there we have three major pillars, basically. The one is mask-based form extraction. And you can think about it this way. If a document has very static type of entities and input that don't change in position, no kind of LLM will ever beat you just knowing the position where usually the name of somebody is. And we do also a lot of dewarping in this mask-based extraction. So even if the document is somehow moved or in some way curved, we can just dewarp the document again, get the perfect positions, and we get extraction accuracies in excess of 95%, even on quite bad salary statements by Datev or something like that. Then a second system is our in-house system. This is a bit of an older architecture, but because of that, it's a smaller system. You have, again, a bird type embedding. On this bird type embedding, you do named entity recognition. And this is highly adaptable. You can train it with very little customer data, about 10 examples per entity. And the big advantage over what is down there, what a lot of people are probably asking, why not use an LLM, is you can use it in-house because it's a lightweight system. So you can train it on customer data. The system can be either hosted on a CPU or on a small GPU, and it gives highly accurate results. And this is, of course, really important for sensitive data or situations where you want to kind of adapt to the customer in some other way. And the third pillar is, of course, something a lot of you have been definitely discussing, large language models, models like GPT-4 or models like DeepSeek. They can simply be prompted to extract the data directly, which also has its advantage. It's very quick. You don't have to have any data at all to adapt them. You just use them. And we have a specialized template for LLM extraction that we can use for all the cases where they are the best way to go forward. Okay, so this brings me to the conclusion of my talk. Overall, we have seen the highly multimodal fingerprints of the documents allow us to have a classification system that beats out a classical AI approach, at least on the data sets we have tried, both of them. It's also quite adaptable. We have a big input management process that we can tailor to whatever needs should be met by a combination of using this classification system and expert extraction systems. And I want to leave you with a quote by Manfred Eigen. I don't think he actually said it. It's apocryphal, but I like it anyway. And he is purported to have said, in a sufficiently high-dimensional vector space, every raindrop finds its way into the ocean. And I want to thank all the people at CIB who helped me build these systems, and we built them together, and the AI team and other teams who helped us. And yeah, I'm waiting for your questions.